Measures of center are ways of describing what? Measures of center describe. Like if I found the mean age in this room was 22.6. It's like an average, but what is an average telling us? We add them all up and divide, but in general, if we say the average age or the mean age is 22.6, most common, typical, it kind of describes in general what's happening with ages. That's what we call it measures of center. It's kind of like what's in the middle. It's not really the middle, that would be the median. But what's typical or common is a good way to think of it. Which is why we have all these different ways. Maybe it's the median, maybe it's the mean, maybe it's the mode. But everything we did in that section was describing what's typical. What we're talking about in 3.2, measures of variation, make sure you recognize that word variation. It will get thrown in here and there throughout the semester. Variation is measuring how things differ from each other, how far apart they are, how much they vary. Vary means how much they change from each other. I'm on top of page 28. Top of page 28, 3.2, measures of variation. So for example, I think I talked about the kindergarten classroom last time, and there's all these 5 and 6-year-olds. Pretend we're not including the teacher now, just a bunch of 5 and 6-year-olds. The average age in there, the mean age is probably 5, maybe 5.5, depending on, I don't know how many people are 5 or 6. But how far away from that are most of the students in there? Let's say the mean was 5.5.
A good portion.
Say that again?
A good portion of them would be about 5.5.
A big part, well, no one's actually, I mean, they could be 5.5, but when we ask them their age, we're just going to take either 5 or 6. But most of them are how far away from that 5.5, like half a year, right? They're either 5 or they're 6. They're not, those ages are not spread out much. If you listed them all in a row, there's a bunch of 5s, a bunch of 6s, and no one's very far away from the mean. We agree with that? So they don't vary much, those numbers. They're all close together. They're all kind of the same. Now, let's say I did it in this room where I just found the mean of 22.6. How much variation do you think you're going to have compared to that kindergarten classroom? A ton, she says. I mean, because there's going to be people, I mean, think about how you are compared to 22.6. I'm sure there's some of us in here who are younger than 22.6, by 4 or 5 years at least. And there's some of us in here that are much older than that. So we'd be spread out by quite a bit. What did you say, Kevin?
I throw it way off.
Yeah, he's offering to throw it way off by being quite a bit above the mean. I'm assuming above, sorry, it could have been below. But that causes this room to have a higher variation. More spread, the numbers are more spread out. You all right on what variation measures? So it's not what's typical, it's a number that describes how spread out they are. So in the kindergarten classroom, maybe I would say the mean was 5.5, and the variation measurement I use is like a 1. Making everyone's around 1 year away from there at most. Where in this room, the mean might be 22.6, and it might be typical to be 5 years away from that. Some of us even more. 5 years away, so the number might be 5. The second number describes how spread out they are. So that's what all of 3.3 is about, measuring the spread between the numbers. So I have these two data sets on the top of page 28. For a little review, I would like you to find X bar for each of those lists. Remember what X bar is?
Mean.
Thank you, it's the mean. And we find the mean by?
Add them all up, divide by the number.
Perfect. Add them all up, divide by how many variables or how many data points you have. We did this last time. So a little review, I want you to find X bar for both of those. X bar is the mean from that sample. Yes?
Does it matter? Is that a -2?
Yes, that's a -2.
So how does that affect the answer if there's a negative?
Well, it doesn't really affect the answer. I mean, it affects the answer because it is negative. When you type it in, you should hit the negative button on the calculator. Because, for example, if you're talking about being, 2 versus -2, one's further away from, say, 1 than the other one, right?
Right.
So it has to be a negative. But negatives are possible. Like if they were, for example, how much money you have. Maybe you owe me $2, so yours would be -2. Or somebody else might actually have $2, they'd have a +2.
So, but it won't affect like the sign on the outcome? Like it won't be negative?
It could, if we had a lot of negative numbers, then the mean would probably be negative. If more people owed money than had money, then the mean might be negative.
Okay.
This one will just bring it down a little bit, but it won't make the whole answer negative. Good question though. Did everyone find the two means? Were they the same? Okay, good. They should have been the same. 8, right? If you didn't get 8 for those two means, double check your work. Means you probably either entered it in your calculator wrong, you read a number wrong. We know how to find the mean. Add first, then divide by 6. Okay. They have exactly the same measure of center. So if I said, here's two lists of numbers, describe what's typical, the answer might be 8. 8's typical in both lists. But those numbers are not, or the lists are not the same. So this is why we always talk about what's typical, what's in the middle, and then we talk about also how spread out they are. Because if you were just looking at those lists, yes, they both have a mean of 8, but which list is more spread out? The bottom one, right? These are all between 5 and 11. Think of a number line. These go all the way down to -2 and all the way up to 18. They're much more spread out from the middle. See what we mean by spread? That's what we're measuring with variation. So there's 3 ways that we're going to talk about measuring variation. You know, last time we talked about 4 ways of doing the center: the mean, the median, the mode, and the mid-range. I went from 3 to 5. I don't know how that happened. But we're going to talk about 3 different ones. The easiest one is the range. The very first thing underneath the list there on your paper, the highest number minus the lowest number. So in this case, the range is 11 minus 5. The range is 6. They're spread out over 6. Like if you were on a number line counting from the lowest to the highest, it's a distance of 6. Be careful. What's the range for the second list? 20. Some of you are getting 16. Make sure you actually subtract 18 minus -2. See if I can squeeze it in here. Minus a -2? Yeah?
Change the sign.
Changes the sign, right? I'm going to put it in another color here. When you're subtracting a negative, that turns it into a plus. So actually your range is 20. If you type it into your calculator, minus a -2, you can handle it as well. So this range is higher than this range. Right, because 20 is higher than the 6, which tells me that the second list has more variation than the first list. The bigger the number, the more spread out they are. We could kind of tell by looking at them, but sometimes the list is so messy that you can't really tell. Everyone agree that you can see the bigger number means they're more spread out? Okay, so that's one way of measuring the variation. The next one is something called standard deviation. I reminded you of the round-off rule there that keeps showing up throughout the semester. Same one we talked about last time. The standard deviation is a little bit tricky to calculate. We're going to calculate it by hand so we understand what that formula means. And then I'm going to show you how to love your calculators. Couple things about standard deviation. It's kind of like the average deviation or the average change away from the mean. So the kindergarten classroom, when I said it's around a 1, everybody on average is 1 above or 1 below the mean. In here, maybe it's an average of 5 or 6 above or below the mean. It might even be more. Some of us are closer, some of us are further. It's kind of like an average, but it's a little bit messier than that. Standard deviation is always positive. You can't get a negative answer. It's 0 if all the data is the same number. So let's say we go back to the kindergarten classroom and coincidentally everybody's 5. If everybody's 5, the mean is going to be 5. And how far away from 5 is everybody? 0. There's no difference between 5 and 5. So 0 means there's no variation at all. The numbers are all the same. The bigger your number, the more spread out they are. And outliers will have a strong effect on it because we include them in our calculation. All right, so let's look at the scary formula. We have S equals this giant square root. We have this sigma sign that we talked about last time. Don't worry, I'm going to break this down. This is the formula for S. Middle of page 28, not quite the middle. Pretty scary. I'm not going to write the other one down, but you can see it in front of you there. Subtle difference. What are the differences between those two formulas? The -1 is missing on the second one.
Capital
A capital N instead of a little n. What's the difference between those? Do you remember?
population sample.
Population versus sample. The capital N is your whole population size. Your little n is your sample size. And the other difference between those two things is, yes?
There's a mu.
There's a mu in that second formula. It's a pretty scary looking formula. And there's a sigma in it too. We call this little guy a sigma. Sigma.
It's the
I can't draw it as nice as the book can print it, or the notes have printed it. This is called the standard deviation for the population. It's a Greek letter. I think it kind of looks like a sideways 6. That's why I try to draw it that way. It's the one next to the formula there. I can't draw it as nice as they do. By the way, most of our Greek letters, if you're trying to type them, we're going to do our projects in 2 weeks. We'll start working on them. They're under the symbol font. All the Greek letters, you just change it to symbol, and we'll change them to the right ones. But we'll talk about that later. So this is the standard deviation for the sample. And this is the standard deviation for the population. Which is why they're using the mu in that second formula, because mu was the mean from your population, remember? Let's just organize those little thoughts for a minute. We had x bar and we had mu. And now we have S and we have sigma. This is what we did last week, is what we're doing right now.
Yep, and two.
Say that again?
Good night.
Oh, and we have N and we have capital N. Thank you. I think those are all the similar yet different things we've seen so far. Someone help me out with any of those.
X bar is the mean.
Well, I need more information than that. Sample mean, right? That's the sample mean? So remember my example was all LMC students? If I just took some of you and averaged your ages, that would be a sample. So that would be X bar, sample mean. Mu would be the population mean. So if I could do all LMC students, we just talked about S.
Standard deviation.
Standard deviation for the sample. So I'm going to write sample standard deviation. I'm just going to leave this over here in this corner for now so that we have it for reference as we go through here. And sigma is the population standard deviation. We have to use a lot of abbreviations to squeeze it
I
in
thought
here.
sigma was E.
Excuse me?
I thought the sigma was like the weird E.
Ah, good point. He said, I thought sigma was that weird E. This guy right here?
Sideways W.
This one? He's right. This is a capital sigma. This weird one right here that I can't draw very well is a lowercase sigma. So you're right, they're both sigma. One's uppercase and one's lowercase. Good memory. We're not going to use that necessarily in my list because it doesn't represent a variable. It just represents telling you to add things. Where sigma represents something. The smaller, lowercase sigma represents the standard deviation. Now, what's the difference between little n and big N?
Sample population.
Sample and population, what?
The number size.
The number or the size? Sample size, population size. So what's going to happen all semester long is I'm going to interchange these expressions and these variables, and you need to know which one is which, because sometimes one makes sense, sometimes the other, and you need to know that the mean is not always x bar. It might be x bar, it might be mu, depending on what you're doing, and same with the standard deviation. Now the reason I didn't copy down the second formula here is number one, this calculation is tedious as all get out. And so just to do it with a small sample is enough work that the population standard deviation is something we will never calculate using a formula. That's why I'm not even going to write it down. It's there for you to look at. We can see the similarities.